Good morning, this is Todd Coburn of Cal Poly Pomona with Aero 3261's Lecture 8 on torsion and twist, but this time we're going to look at thin-walled closed sections. Here's how it works. We already have seen how if we have a circular cross-section loaded in torsion, whether it's solid or hollow, how our shear stress is TR over J, our angle of twist TL over GJ, with polar moments of inertia as shown below. And we know the assumptions associated with those. Then we learned about non-circular sections, both singular and composite sections, one made of multiple flanges. We have seen the assumptions that are now different. We have seen the equations. Shear stress is now TT over J, where we have a different torsional constant with an alpha and a beta for stress and angle of twist. Angle of twist is still TL over GJ with a different constant, and we talked about how to idealize those sections. Today we're going to look at a different kind of section as shown here. All right, in order to understand this, let's take a look at a little cross section. This is something like what we might see in a wing where we have a thin-walled section that's closed. I'm going to redraw it. This is our member. You can see we have a torque applied back here, and we have a cross section that we're now redrawing there, and I'm going to redraw it down here even larger. Okay? We have this general area here, and if we focus on a little element of length ds, now our assumptions are that the ends are free to warp and that our shear flow is constant, which means the shear flow all along here doesn't change as it goes around the thing, okay? This is a common assumption we're going to use when we have thin webs. So we have a shear flow going like this through this little segment. In fact, it's going all the way around, but I'm not drawing them all. Now, if this is ds and this little shear flow is q, and if we go and we sum it around here, now we could say the total force on this little segment here is just q ds, right? The force P is just q ds. And if we call this point O, the perpendicular distance to that force we're going to call h, as we see over here. You see that? See both of those things? All right, so we can write then that the total torque caused by this little segment right here is just going to be this force times this perpendicular distance. This is the force, and this is the perpendicular distance. That's the total torque or moment, the change in moment for that. Now if you look at this a minute, you take a look at this ds and this h, you notice this little area here, this enclosed area, if we just take a line from this point O and draw it to the first part of the web and draw another one to the other part of the web, that has a little enclosed area A. The area of that, as with any triangular member, is ds times h. So the area enclosed is ds times h over 2, right? Since it's a triangle, over 2. dsh over 2. That's the area enclosed. Now if you look at this, we have ds times h here, which is actually twice the enclosed area, where this area is not the cross-sectional area. It's not that area. What we're talking about is if you draw a line through the center line of this, we're talking about the enclosed area there. So actually we can write this is the same as 2 times the enclosed area times q, or q times 2 enclosed area. You see that? That's the enclosed area of our little segment here. Now, if we continue on, the total torque is going to be the summation of these for all the little areas, this little all area as we go around, which means that this is equal to 2QA. Now here's where I'm going to, well, I'm not going to yet. What this means is this 2QA here, this is the total enclosed area through the center line distance. So we find the center line distance, take the total enclosed area. That's what that is. Let's erase this crap and now look at this. So our total torque is the summation of the two QDAs. If you sum those up, we just end up 2 QDA, which actually is Q times twice the area. This is a key equation. This area then is the area enclosed by the mean periphery. So let's take a look at this a minute. Let's say we have a section that looks like this, and this, and this. What we would do is take the area enclosed by the middle of this, midplane of those, the area enclosed by the midplane of those, the area enclosed by the midplane of those. Those are the areas we're talking about, and we have the relation that the torque on the section is equal to the shear flow times twice the area. This means that the shear flow is equal to the torque over twice the area. These are two relations that are very important and make the analysis quite simple for analyzing thin-walled sections like these. So these two relations, we know that from before, from shear flows, we know that our shear stress is just the shear flow over T. I told you that the shear flow that we sometimes use an N for, we often use a small q for when it's a shear one. And so we can write our shear stress as T over 2AT. It's actually better nomenclature to say that the torque is 2QA and the shear flow is T over 2A and the shear stress is Q over T. These are key relations that we're going to use over and over in aerospace or actually any kind of lightweight structural analysis. So we know how to analyze solid and hollow circular sections. We know how to analyze non-circular sections, and now we know how to analyze thin-walled closed sections. Now if they're open, they become a non-circular section. If you take a round section and rip it along the length, it's now an open section of this length. This is the B and that's the T. Let me show you that. This can be analyzed as a circular section or as a thin-walled closed section. This can be analyzed as a thin-walled closed section. This has to be analyzed as a thin-walled, as a non-circular section where we're going to have B and T, B and T, B and T. It's going to have a very low shear stiffness. This thin-walled closed section, this is a non-circular section because it's not closed. It hasn't closed that circle. Okay? Got that? All right. With that said, we now can extend this further. Now, to get the angle of twist, we're going to have to do a little more work. Going back to our shear element, remember, this looks like a shear element. If you take a look at this, remember a shear element looks like this. We have a shear stress like this, and since they're romantic, they go like this. That's what we're seeing right there. We have a little distance ds from here to here, and this is just 1. We see into this action of the force, we're going to get a little resistance. This is our little shear strain, right? So where the force on this leftmost edge is just QDS. These are the ideas we're going to be using to develop our angle of twist. We know that the energy is just force times distance. Now the force is just QDS, but if it's in the elastic range, the energy is QDS right over 2, right? So the force is QDS, that little deflection, since our shear strain is the deflection in this direction for a length in that direction, our shear strain actually is equal to the deflection caused by this shear force in the same direction as the shear force QDS. So actually this energy is QDS times gamma, and because that's the force times deflection, but because it's elastic, it's building elastically, we have that 1/2 term as we saw before. So that's the energy per unit length We know that the shear strain is given by the stress over the modulus of rigidity, which we can write this way, which we can write this way, which we can write this way. If we plug that in, we get that the little increment of energy is q ds over 2 times gamma. Plug in those values, and we find this relation here. Now, if we want the total energy on the section, we would then take the summation of those, which we can do with an integral or with a summation, and we have to do that with a double integral because we've got ds and dx over the entire length. That u prime is the energy, strain energy per unit length. If we want the total strain energy in the entire member, we've also got to integrate along the length, which gives us the double integral. And from Castigliano's theorem, which you haven't learned yet, we can apply that, which basically says that the angle of twist is just the change in energy with respect to the change in torque. That's the torque, not a temperature, which you can write this way. And this way, we're actually going to learn Castigliano's theorem at the end, but I'm actually using it here to develop the derivation of what we're doing. And we end up with this equation here, which basically says, through Castigliano's theorem, that the angle of twist of a thin-walled closed section is just the shear flow times the length over 2 times the enclosed area times the modulus of rigidity, and then the summation of the ds's over t's. Actually, it's a little better formulation to put the q inside the summation. It's q times the ds over t. But if we have a constant shear flow with a single web, as we do in this case, then we can actually pull that q out of the integral. What does that mean? That means this. If we have a section like this, let's just say it's really thin, and those are the dimensions, and let's say it's carrying a shear flow Q, like this, okay? Then actually, if we want the angle of twist, we're going to take that shear flow Q, we're going to take the length, that's the length going into the page, so if we look at this thing, if it goes back into the page like this, this is going to be the length going this way, right? We're going to have 2 times the enclosed area. What's the enclosed area? It's this value. So in this case, it's B times H, right? This is the A enclosed times the modulus rigidity. Then we're going to have the summation of the Q ds over T, okay? Now, we I put Q here, so if we take that into here, we're going to have Q times ds over T, right? Well, what's the Q ds over T? Let's just continue this. L over 2AG, and now we've got the summation. So what we're going to have is the shear flow in this web, Q, times its ds, let's call this B, over its T, plus the Q again, times this little distance, which is H, over T, plus this one, which is QB over T, plus, and this one, QH over T. That's the summation. Looks like we've got all the terms. This value is our angle of twist in radians. And we can convert that to degrees in the normal way. Does that make sense? Don't worry, we'll look at some more examples. Stand by. You can also write it this way. This is actually, writing in this form is more useful when we're solving multiple cell webs, which we're no longer covering in this class. Okay, so just to summarize, here's our shear assumptions. This is our derivation. We have our torque, and we have our key equations, okay? These values, this kind of summarizes everything we just learned about thin-walled closed sections. Okay, let's take this further, and if we take a look at what we talked about a moment ago, let's say we have a thin-walled section. Now that can be idealized like this or like this. This one on the left can be either analyzed as a circular section or as a thin-walled closed section. This one on the right, because of this cut, has to be handled as a non-circular section. The B of that is going to be just the circumference. If this gap is negligible, it's just going to be 2 pi r or pi d. And we then can calculate the torsional constant. The torsional constant for the one on the left is this. The torsional constant for the one on the right is that. From where C1 is just our alpha or beta, okay? This is the nomenclature out of your Barron-Johnson supplementary text. If we take the ratio of the torsional constants, we find that a closed section has something like 584 times the stiffness of this for this example here. What that means is, as soon as we cut this web, it's really flimsy. Now, this doesn't mean we punch a hole in the side of the web, like if we had, let's say, a section, let's say we have a rectangular wing section that looks like this, and some idiot pops a hole in this section right there. That won't be a problem. That will cause other problems. We should put doublers and things around there, but that doesn't make it a non-circular section. But if a crack runs along the length of it like this, that splits the whole thing, now this is a non-circular section. That's what we're talking about. Got that? All right, let's look at some example problems. So here's our first problem. We got a little part. We got some little dimensions here. Looks like the thing's about 100 inches long. And we want to know, we got the shear flow is 500 pounds per inch uniformly around it. We want the shear force in web A. What's the shear force in web A? Well, it's just going to be the shear flow times the distance, right? Boom. What is the shear force in web J? Once again, shear flow times the distance. Happens to be this distance is the same as this distance. What is the shear stress? Well, that's just the shear flow over T, right? Which is just 500 over whatever thickness. How about the torque? Let's say we want the torque around point A of something. Let's say the torque on the whole section is just going to be 2QA, right? Boom. What's the torque that web B, that means whatever force is in this web B, induces around point A. Well, we'd have to take the force in web B and multiply it by the perpendicular distance. Or we can use, that's what the second one's doing, it's calculating the force in web B times the perpendicular distance. That means Q times 10 times the perpendicular distance 10. Or we can use the shear flow equation. Remember to use that if we want the shear flow that just, remember what we're saying here. Let me redraw the section here in like hidden lines a little bit here. This is the section we have. We're talking about this web right here. We're saying, what's the torque that this web induces around this point A? Well, we have a shear flow here, Q. The force in that flange is just Q times ds, which is just Q times 10. That's the force P in that flange. The perpendicular distance is just 10 inches, right? That's what this equation says. Or you can use our other equation, 2AQ, which basically means you're saying, okay, we're going to sum about here, so we're going to draw a line from this point to this end point of the web, draw it through that end point of the web. This is the enclosed distance. So we're going to say that the torque is equal to 2AQ, where 2A is going to be 10 times 10 over 2 times 2, right? And then we've got our Q. That's what these two ways of calculating the torques around that point. Make sure you understand this. If you just glaze over and just go, yeah, makes sense, without thinking about it, you're going to get stung when I go and measure you, okay? Another problem. Here's another similar problem. Now we got some thicknesses and a torque applied. What's the shear flow? We just apply our T over 2A, where we take the total enclosed area 10 times 10. Now you can kind of tell with these webs, they're so thin, we can't even tell the distance of these dimensions to the outside, inside, or to the middle. Really what we're talking about here, we're talking about enclosed distance, we're talking about mid-plane distances from the webs. But if our problem is, the thinner our webs get, the less that actually, the less the difference between the outer, inner, and mid-plane matters. So a lot of times we'll just sloppily just call that the dimensions as we show here. Okay? What's a shear stress? Just Q over T. Angle of twist, we'd say, all right, we've got Q, everything's 50 all the way around, right? You calculated that down here, times the length, 100 inches, divided by 2 times the enclosed area. What's the enclosed area? It's just 10 times 10, right? There's our modulus, and then we have our summation of the ds's over T. Well, the ds's is going to be 10 over this thickness of B, the length of A over its thickness, the length of J over its thickness, the length of F over its thickness. In this case, all those lengths were the same, but we could have different lengths, different thicknesses, and we'd sum it up like this. Problem 3, Here's a similar problem. What's the shear flow? Once again, we're going to follow the same procedures. It's starting to sound like deja vu. Okay. If we have a part like this, now we can actually, even though this is a thin-walled section, we can actually see there's a difference between. What we're going to need to do is calculate what our mid-plane distances are, which means we're going to want to calculate what is our, if we look right, right through here. So if that's 4 inches, then the distance from here to here, and this is 0.16, is going to be 4 minus 0.08 minus 0.08, right? This one is going to be 2.5 minus 0.08 minus 0.08, and so on. Okay, we're going to need those numbers later. You should already be looking at that and thinking that. Okay, so we're going to calculate all this, calculate the enclosed area, calculate the shear stress, shear flows, and angle of twist. That's all I got for you. Enjoy.